Let's do some questions for the physics midterm. So a car is traveling on a straight road 15 meters per second and accelerates uniformly to 21 meters per second through 12 seconds. So what is the total distance that's traveled by this car? So pause the video for any of these questions, honestly, and try them out yourselves before I do the answer. Okay, so what is the acceleration? Well, we know that acceleration is equal to basically velocity over time, right? It's the change in velocity divided by the change in time. So the change in my velocity, well, it goes from 21 to 15, or sorry, 15 to 21. So that change is 6. And this is over a period of 12 seconds. So therefore, my acceleration is 1/2 meters per second squared. And all this is saying is that, well, basically every second that passes, my velocity is increasing by 1/2 meters per second, half meter per second. Now to find a distance, well, you might remember, or displacement, whatever, you know that you got this kinematic equation to help you, right? Your displacement is equal to VIT plus 1/2 AT squared. Therefore, what's my initial velocity? Well, it's originally 15 meters per second, and this is over 12 seconds, right? Times 12 seconds. And this is 1/2 times the acceleration, which we just found out, times time squared. So let's plug all this into the calculator. So after just plugging everything into the calculator, I got 216, which should be the answer. Number 2, a baseball player runs 27.4 meters from the batter's box to the first base, overruns the first base by 3 meters, and returns to first base. Compared to the total distance traveled by the player, the magnitude of the player's total displacement from the batter's box is blank. So let's draw a diagram to visualize what's happening. So you have this person. He's going to first base, right? So this is baseball. You got your first base here, and this is 27.4 meters. However, this guy oversteps it by a length of 3 meters, right? So this guy kind of oversteps it by 3 meters. So he's going 3 meters forward, but then he realizes he's gone too far. So then he goes 3 meters backwards. So what is the total distance traveled by the baseball person? Well, he ran 27.4 meters, then 3 meters forward, then 3 meters back. And remember that distance is kind of the total length, right? It's the total path that he ran. So in total, how much did this guy run? Well, this guy ran 33.4 meters, right? Because that's the total of all of these things added together. But what about displacement? Displacement only cares about your initial position and your final position. And notice how your initial position and your final position, well, that's only a length of 27.4 meters. So the difference in this is going to be 6 meters. And of course, the displacement is 6 meters shorter than the distance. A blinking light of constant period is situated on constant velocity. So a blinking light, it's constantly blinking, right? It's at a constant rate. So you have light that's blinking at a constant rate, but you also have a lap car that's also moving with constant velocity. So answer choice C here would be the correct answer because, well, the car or whatever, it's not speeding up at all, right? It's just maintaining the same pace, and so is the light, right? Every time the car moves and every time the light blinks, it's always at a constant rate. So nothing is speeding up or slowing down. So you would actually find out that the intervals between the light blinking and everything, they're just going to stay constant. Base your answer. So you have a 1,000 kilogram car traveling at 20 meters per second, decelerates until it comes to rest. And you want to find out the total distance the car travels as it decelerates to rest. Okay? Well, here I want to find out the distance using this formula. Once again, it's equal to VIT plus 1/2 AT squared, right? AT squared. That's the formula that I want to use. But the problem is that I know my initial velocity and I know my acceleration because we're decelerating, but I don't know the time. So is there any way that I can solve for the time? And the question, or the answer to that is yes. Recall this formula, right? Anytime we accelerate, that's going to cause a change in our initial velocity. And the amount of time that we're doing that acceleration or deceleration also influences that final velocity that we get. So what do I mean by that? Well, our initial velocity is 20 meters per second. So our initial velocity is 20 meters per second, and we're decelerating by -5 meters per second, or second squared, or we're accelerating by -5 meters per second, so we're decelerating, and we want to find out how much time does that occur. Now, the important detail to note here is that we're decelerating until we're going to rest, and when an object is at rest, they ain't moving, so it's going to have a velocity of 0. Now we can solve, and when you do this simple algebra, you're going to get that the time is equal to 4 seconds. Now, why does this make sense? Well, think about it. You're going 20 meters per second, but you're decelerating by, 5 meters per second squared, or you're accelerating by -5 meters per second squared. So every second that passes, our velocity is decreasing by 5 units. So after 1 second, our velocity is going to be 15 meters per second. After 2 seconds, it's going to be 10 meters. And you can see the pattern, right? 3 seconds, 5, 4 seconds, then we're at rest. So you can see how it takes a total of 4 seconds in order for our object to completely come to rest. And now that we have our time, we're just going to plug it into this formula. So this is going to be equal to our initial velocity, which is 20 meters per second multiplied by our time plus 1/2 times our acceleration, which is -5 times our time squared. 4 squared is 16. And doing all this on the calculator, I actually got 40 meters. So that will be the answer. Starting from rest, an object, sorry about that. An object rolls freely down an incline 10 meters in approximately 2 seconds. The acceleration of the object is approximately what? So we have an incline that's 10 meters. Let's just say we have some sort of object, let's say a ball, and it's rolling down this incline in 2 seconds. So it takes 2 seconds to do this. And we want to find out the acceleration of this object. Now, I already see a problem. Acceleration is measured in meters per second squared, but 2 of the answer choices are in meters per second, which are the units for velocity. So I can immediately get rid of those 2 answer choices. This problem is the same concept, so it's going to be this formula right over here, plus 1/2 AT squared. But the thing is that our object starts at rest, right? Because we're starting at rest. So our initial velocity is 0, so we can kind of just get rid of this term. And then we just solve here by plugging in everything. So d is 10, our time is 2, and 2 squared is 4. And acceleration would be 5 meters per second squared. An object accelerates uniformly from rest, and this is to a speed of 50 meters per second in 5 seconds. So what is the average speed of this object? So we're going from rest, so our initial velocity is 0 to a speed of 50 meters per second, and then this is occurring after 5 seconds. So we want to find the average speed of the object over this interval. So how do we do that? Well, average speed, well, that's going to be basically just literally the average speed, right? It's going to be the average of the final velocity and initial velocity divided by 2. All right. And the reason why we can use that formula is because we're accelerating uniformly. So you can imagine a graph. Let's just say if we're plotting velocity over time. So this is our velocity, and this is changing during a period of time. And because we're accelerating uniformly, right? So we're accelerating at a constant rate. You can imagine that our velocity is increasing constantly. So the average is just going to be the average between the final and the initial velocity here. A child is riding a bicycle at 15 meters per second. Decelerates at rate. What is the child's speed at that? Oh, well, if we want to find out final speed, given some time, given some deceleration, and given some initial velocity, what equation contains all these variables? It's going to be this equation, right? So our final velocity, well, that's what we're trying to find out, right? Initial velocity, that's going to be 15. Acceleration, oh, it's decelerating. Got to put a negative sign in front, right? Sometimes acceleration isn't forwards, rather it's in the opposite direction of what you're heading. Like think about a car and you're pushing on the brakes, right? So you have a car, velocity is moving this way, but your acceleration is moving the opposite way because you're trying to slow down this car, right? You're trying to decrease that velocity so your truck or car comes to rest. So whenever you hear deceleration, you should be thinking negative sign or just the opposite direction of, where you're going. And the time is 4 seconds. And I don't know why I put VF is equal to 0 here, but it should just be VF. So now we can just solve for this, and we get 3 meters per second as our answer. A rock is dropped from a bridge. What happens to the magnitude of the acceleration and the speed? So whenever you have an object in free fall, which just means that gravity's just taking complete control over that object, your object is going to increase the speed, right? Your velocity, let's say this is at the velocity at some specific time period, v of t, and let's say this is the object's velocity, let's say, I don't know, v of t plus some amount, v of t plus 1. Notice how the object is getting faster, but the acceleration due to gravity stays constant, right? The acceleration due to gravity is constant. It's 9.8 meters per second squared. So acceleration remains the same, but the speed increases. So D would be the answer choice there. Base 2 kilogram mass. Halfway down, the acceleration is what? Once again, acceleration is going to be constant. It doesn't matter if the object is heavier, or I don't even know. Like, if we're ignoring air resistance, if you drop two objects with different masses at the same time, they're both going to land at the same time on the ground. This is due to Newton's second law. You might think that a bigger object would just be falling like quicker, but the thing is that bigger objects also have more inertia. So think about it like this. You have a small object which has a pretty small force of gravity, and the force of gravity is different from the acceleration due to gravity, so keep that in mind, right? The force of gravity is literally just, you can think about it as just the weight of the object, right? So the weight of the object is just equal to mass times this gravity constant. So it's equal to mass times this gravity constant, which in this case, gravity represents our acceleration. So this is just force is equal to mass times acceleration in disguise. And let's compare this. So this is object one, and let's compare this to object 2, who has a way bigger force of gravity, but the mass is also bigger. So notice how the acceleration stays constant because the force due to gravity and the mass, they balance each other out. If you have a small mass, the force due to gravity is going to be pretty small, so this gravity stays constant. Meanwhile, because this object has a large mass, the force due to gravity is big, but that's balanced out, right? These two things balance out, so the acceleration due to gravity is going to stay constant here. So this is due to Newton's first law, the law of inertia. Bigger objects, they have more resistance to change. Graph below represents the relationship between speed versus time. What is the total distance traveled by the object for the first 4 seconds? How do we do this one? I know that speed is equal to distance over time. So if I multiply speed and time together, I'm going to get the distance. But how do we do this for a speed that's constantly changing? Well, consider a graph like this, where the speed is constant. So let's say if this is going on for 5 seconds, and let's say that my speed is 4 meters per second, and I want to find the total distance. Well, what do I do? Well, I know that, speed, which is 4 meters per second, multiplied by my time, 5 seconds, that's going to give me a distance of 20 meters. So my distance would be 20 meters here. And notice what I'm doing when I'm doing speed multiplied by time. I'm essentially just calculating the area underneath this curve, right? And that's the same strategy that we do here, right? So in this case, I'm trying to find out the total distance during the first 4 seconds. And that is literally just going to be the area underneath this curve. All right. So it's the same intuition that you would use for simpler problems like this. So I know that my triangle is 4 times 20 divided by 2. So I'm going to get an answer choice of 40 for number 16. Okay. And wait, I think I kind of skipped a page there, but that's fine. The graph below shows the relationship between speed and time for first object. Object of the object of the acceleration of object A is blank. How do I do this? How do I do this one? Well, you have two objects, A and B, and we're comparing their accelerations. Now, whenever I see speed over time, that makes me think about acceleration, right? Because acceleration, the definition of it is velocity over time, or speed over time, whatever, right? And the reason why I say whatever is because don't forget that velocity, that's a vector quantity, and speed is a scalar. But a lot of times in the regions problem, they kind of use that interchangeably because like objects sometimes just only head in one direction, so the net speed is equal to kind of the net velocity. So that's why I'm kind of using those terms interchangeably here. But if we're comparing the accelerations, right, that's literally just going to be the slope of this line. Because think about it. Slope, change in y over change in x. What's our y value? That's speed. What's our x value? Time. Speed over time. That's acceleration. If this was, let's say, distance, well, distance over time, that would be a velocity slope. This slope would represent our velocity. All right. So that is how you can kind of interpret these graphs. Now, we're just going to be comparing the slopes now, right? So 10 over 4, that's a slope of 2.5. So that's for B. Now for A, how do we do this? Just leave this small. I mean, because our acceleration is constant, I can kind of just pick any 2 points. So let's just pick these 2 points because it's easy. So we have 15 divided by 2. And this the slope of our line, because our second point starts at 0, 0, right? It's just 15 divided by 2, which is 7.5. So object A would be 3 times as great because 7.5 is 3 times as great as 2.5. So 17 would be C. Below velocity of this. What is the recoil velocity of the cannon? Whoa, this one's pretty cool. This is the conservation of momentum. So remember, momentum symbolized by P is equal to mass times velocity. And this indicates how hard is it to stop an object. If you have an object that's super big, that's harder to stop. If you have an object that's faster moving, it's also going to be harder to stop because inertia, right? So momentum describes how hard it is for an object to start moving. And in a lot of these regions problems, they like to test you on the conservation of momentum. So basically the momentum before is going to be equal to the momentum after. All right. So let's see how this plays out. So originally, right, everything was at rest. My momentum before is 0 because everything is at rest. And that means my momentum after also has to be equal to 0. All right. Now the momentum after everything is composed of the mass times velocity of the cannon plus the mass times velocity of the cannonball, right? Because the momentum, the total momentum is equal to the sum of the momentums of the objects comprising this system. So the total momentum would be the momentum of our ball plus the momentum of this cannon. However, both these things weren't moving initially, so that's why I said this is equal to 0. But there are some things moving at the final state, which is why I'm focusing on this part. Now, our cannon has a mass of 1,000 kilograms, and we're trying to find its velocity, right? So we can just set that to our unknown. The mass of our bowling ball, not bowling ball, but whatever that is, it has a mass of 10 and a velocity of 500. 10 times 500 is 5,000. I push this to the other side, so I get negative 5,000 is equal to 1,000 times my initial velocity. And if I divide by 1,000, I get that not my initial velocity, but the velocity of my cannon, that's going to be negative 5 meters per second. And this makes sense because, of course, our cannon is moving backwards. So it makes sense that we got negative 5. And in case of you guys wondering why this is 5 meters per second, well, you can think about it as, because this velocity already has an arrow pointing this way, this is the same thing as saying that the velocity of negative 5 meters per second, or actually, let me actually just resolve this. And we can do a little topic on direction, but the velocity of negative 5 meters per second to the right, that's actually the same thing as 5 meters per second to the left, right? Because they're just opposite directions, right? But then we kind of flip the negative sign to a positive sign because the directions change. So because this velocity arrow is pointing to the left, we can already assume that, well, our velocity is going to be 5 meters per second to the left. Okay, so 5 Newton ball, 10 Newton ball released simultaneously. And in case you're wondering why they give the ball or they describe the ball in newtons, is because that represents the weight of the object, which is just the mass times that force or the acceleration due to gravity. So that is what they mean by newtons. That's the weight of the object. Neglecting air resistance, what statement is true? Well, no, the accelerations are all going to be constant, right? Because if the two objects, once again, they fall down, doesn't matter their masses, the acceleration due to gravity is the same. And oh, now they're comparing their momentums. So which one of these objects is going to be harder to stop? The bigger object or the smaller object? Well, momentum is comprised of the mass times the velocity. So of course, bigger mass, bigger momentum. And this is why the answer choice is C for number 19. It's because the bigger object simply just has more mass, so therefore more momentum, okay? And bigger mass, so you can think about it as if the force of gravity is bigger, that means that the mass has to be bigger because this value is a constant. So bigger Newton ball just means that, you can think about it as a bigger mass. A force of 6 newtons changes the momentum of a moving object by 3 kilograms times meters per second. How long did the force act on the mass? So whenever you apply a force over some time period, that's going to cause an object to change its momentum. So if I have, let's say, a bowling ball, and I continue following the bowling ball by, I keep on pushing that bowling ball with some applied force for like a long period of time, well, what's going to happen to the bowling ball? It's going to start increasing that acceleration, right? So therefore, because acceleration changes, that's going to cause a change in the velocity. And of course, velocity, that's related to the momentum. So in summary, applying a force is going to change the momentum of an object after some period of time of applying that force. So this is something called impulse, which has the unit J. I don't know why it has the unit J. We know that the force is 6 newtons. We're trying to find out the change in time. But we do know that the change in momentum is going to be equal to 3. Therefore, the time is 3 divided by 6, which is 1/2 seconds or 0.5 seconds. So number 20 is going to be D. A 5 kilogram car moving at a velocity of 4 meters per second is brought to a stop in 2 seconds. And we want to find out the magnitude of the average force used to stop this car. It's brought to a stop. So I know that initially the velocity is 4 meters per second, but then after it's brought to a stop, that velocity is 0. It's occurring over 2 seconds. So time is equal to 2 seconds. Now, we have all our ingredients to kind of use our initial formula to solve it. So force is equal to, or force times the change in time, which we know is 2, is equal to our change in momentum. Change in momentum, remember the definition of momentum. That's just mass times velocity. So the change in that momentum is going to be equal to the mass times the final velocity minus the mass times the initial velocity. Now, our final velocity is 0. That cancels out. Our mass, well, that's going to be 5 kilograms. And our initial velocity is going to be 4. So therefore, 5 times 4 divided by 2, that's going to lead me to an answer of 10. All right. And I know that this is negative 5 times 4, so technically this is negative 20, and then that should be negative 10 newtons as the force. But this is saying the magnitude of the average force. So whenever you're talking about things in terms of magnitudes, you're ignoring the signs. You're only caring about how large that quantity is. So you ignore the sign in front of that. When a 1 kilogram car moving with a speed of 0.5 seconds, 0.5 meters per second, on a horizontal surface collides with a 1 kilogram car initially at rest, the car is locked together. So this is an example of something I like to call sticky momentum. Sticky momentum is different from regular momentum. It's when you have an object, crashes into another object, and what happens is that these two objects will stick together and they will move together at some velocity. Now, this momentum right over here means that the collision is elastic, meaning that kinetic energy is conserved. But for sticky momentum, the formula is a little bit different. It's going to be m1 v1 plus m2 v2, and these objects are going to stick together. So what's going to happen is both of these objects will move at some kind of final velocity together, which is why I'm multiplying everything by this final velocity. So these are the two important formulas that probably should remember. So in this case, 1 kilogram cart, 0.5 meters per second. So 1, our mass times velocity, 1. I'm using this formula, by the way. So mass times velocity, 1, plus mass 2 times velocity, 2. But in this case, our second 1 kilogram cart is starting at rest. So this term is going to zero out. And that's going to be equal to the combined masses. So I just add up their masses. So what's 1 plus 1? That's 2, multiplied by some final velocity. And if I divide this by 2 to get the final velocity, I get that this is going to be equal to, well, 0.25. Answer choice C for number 22. Now let's do number 23 together. So just delete all of this. It's getting kind of messy. Number 23. This guy is standing at an elevator that is accelerating upwards. The upward force of the elevator floor on the person must be what? So take a look at this. Imagine you're a person standing in the elevator and your weight is 750 newtons. However, the thing is that you're moving upwards. So this upwards force has to be greater than this force that you exert downwards on Earth. So answer choice for number 23 is going to be D, because in order, right, this is your weight, right? The weight of basically, your weight of yourself, that's going to cause, a force downwards. So that means that whatever force is pushing you upwards has to be greater than this downwards force in order for, everything to work out. This is why you might sometimes hear people saying that the net force, this net force is upwards. All right, there's a net force upwards, which is why the person is moving upwards. Oh, that's what happened. Number 10 is here. Okay. This looks like some nice kinematics, projectile motion type of problems. So this looks nice. Okay. A ball is thrown vertically upwards with initial velocity of that. What is the maximum height reached by the ball? Okay. So there are two steps that I kind of do to solve this problem. So let's say if I just throw a ball, right? Now, let's say that I focus on, if I focus on the vertical component of the ball. So I only care about how high the ball is going, or now how far it's going. Now, in the y direction, notice how at the top of this peak, your velocity in the y direction is going to be equal to 0, because that's when the ball is changing from moving upwards to moving downwards. And at this specific maximum height, your velocity in the y direction is equal to 0. Now, another important factor that you have to take into account is, of course, the time. How long does it take for you to reach this maximum height? So not only do you have to find the distance here, but you also have to find out the time. And once you solve for the time, well then, you already know the drill here. Once you solve for the time, I'm just going to plug it into this formula to solve for the displacement, distance. So our initial velocity is 29.4 meters per second. Now, we know that our ball is going to be accelerating downwards in the y direction by 9.8 meters per second squared, right? Because that's the acceleration due to gravity. When we throw the ball up, our ball is going to immediately start accelerating downwards at a magnitude of 9.8 meters per second squared. And we're trying to find out the time it takes for this to happen. And remember that the final velocity in the y direction, if we reach the maximum height, that's going to be equal to 0. So now, solve this, right? 9 divided by 9.8. That's going to be equal to -3. Or sorry, that's going to be equal to 3. So our time is 3 seconds. All right. Now all we have to do is use this formula right here and just plug and chug everything. So let's do that. Displacement is equal to initial velocity, 29.4, times time, plus 1/2 times our acceleration, times 3 squared, which is 9. 29.4 times 3 plus 0.5 times -9.8 times 9. That's going to be 44.1. which is answer choice C right there. A rock falls from rest at a vertical distance of 0.72 meter, surface planet in 0.6 seconds. So from rest to a vertical distance of this in this many seconds, and we want to find out the acceleration due to gravity on this planet. So how do we do this one? We're given some sort of distance, acceleration from rest, so initial velocity, and we want to find out acceleration. Well, once again, it's just the same formula, and because we're falling from rest, we can ignore the first term like we do usually for these problems, but not always. So 0.7 times 1/2 times a times 0.63 squared. I'm just plugging all of this into the calculator now. I got around 3.6 for number 11, so that's answer choice C. As shown in the diagram below, a student is standing on a roof of a 50 meter high building, and he kicks a stone at a horizontal speed of 4 meters per second. How much time is it required for the stone to reach the ground level below? Now, think about it like this. Our velocity is only moving to the right. So how fast we kick the stone doesn't actually matter. What matters is actually just the height of the building, right? Because if we're, of course, in a higher building, then the rock is going to take more time to fall down. But how fast we kick it in the vertical direction doesn't matter. Or sorry, the horizontal direction doesn't matter. What will matter, in some cases is, let's say if you're the person and you throw the rock directly downwards. So you just kind of like slam it down you're kind of like, let's say this is the person, this is your rock, and you just kind of like throw it downwards, like slam it down. Then obviously that would have an impact on, how fast the rock moves down. But the horizontal direction is completely independent from the vertical direction. That's why when you're using kinematic equations to solve this, right? That's why you're using kinematic equations to solve, these types of problems. Sometimes what people write down is the displacement in the y direction is equal to the initial velocity in the y direction times 1/2 times the acceleration in the y direction. Or if you're referring to the x direction, all these would be in the x direction. Okay, so let's get started. What is the displacement? Well, we're going 50 meters downwards, so our displacement is actually -50. And this is the part where people kind of get confused because we're throwing the rock downwards. So remember that your displacement has to be kind of like, it has to be accurate to the coordinate system you're using. So if you're defining going upwards as being a positive direction, then if you do something downwards, then that's going to have a negative sign associated with it. So our initial velocity in the y direction is 0, right? Because we're not moving in the y direction at all. And then this is going to be equal to 1/2 times the acceleration in the y direction, which we know is -9.8 because we're moving downwards, times t squared. So -50 divided by 4.8. I got around 10.2 seconds. Or actually, man, I almost made like a crazy big mistake. It's not 10.2. Because what I very mistakenly forgot to do, and I kind of forget to do sometimes, is remember this is equal to t squared, so I kind of had to just square root it, and it turns out square root 10.2. When I square root 10.2, then I get, okay, then I get 3.19. Yeah, that seems more right, because like 10.2 seconds to fall from a 50 meter building, like at first that just like did not seem right. Okay. That's better. Okay, the ball is thrown horizontally at a speed of 24 meters per second from the top of the cliff. If the ball falls to the ground 4 seconds later, how high is the cliff? This is like the same problem we had before, except this time we're given the time, but we're not given the height of our building, cliff, whatever. So we're trying to find out the displacement this time. And this is going to be equal to our initial velocity, which we don't have an initial velocity in the y direction because we're throwing it horizontally, not in any of these, not up or down, so that's completely irrelevant to us. And this is just going to be equal to 1/2 times at squared. 1/2 times 4 squared, so that's 16. That's going to be equal to 78.4 for, or negative 78.4 for our displacement. All this is saying is that for our building, when we throw the rock downwards, it's going to be traveling 78.4 meters downwards. And that means that the height of the building itself is 78.4, right? So number 13 would be answer choice C. The graph moving below represents the displacement of an object moving in a straight line as a function of time. What is the total displacement traveled by the object during the 10-second time interval? This one is pretty tricky. Well, I mean, it looks confusing at first, but at the 10-second time interval, the displacement is just 8. So, for this type of problem, you kind of just have to look at it, right? So no more calculating the area under curves or any of that. Sometimes you do have to calculate it, but sometimes it's just, easy and simple like this. All right, which graph best represents the motion of a block accelerating uniformly down an inclined plane? Accelerating uniformly. So which answer do you think this one would be? Well, obviously, if the distance is staying the same, our object isn't accelerating. And so is this. This is not uniform. So this is going to be between B and D. B represents constant velocity, right? Because our slope is constant. And remember, distance over time, velocity. But the thing is that this shows constant velocity. And when the velocity is constant, right, think about just a car just chilling down the road. The velocity is constant, but the car ain't accelerating. So whenever you have a distance over time graph that just looks constant, that means that there's no acceleration at all, but there is a constant velocity. So therefore, the answer is actually going to be D. All right. If you actually graph out time versus velocity for this graph, then it would look like a straight line. And then if you graph out time versus acceleration, then it would look like a straight line for this graph. And think about why this makes sense, right? If distance versus time is quadratic, that means that your object is speeding up, right? You're covering more distance as time goes on. So therefore, your velocity is going to be constantly increasing, and therefore your acceleration, that change in that velocity rate, is going to be constant, right? Your velocity is going to be changing at a constant rate, which is literally just the definition of acceleration. Let's actually move a bit quicker past these problems. Let's try to speed things up a bit. Small planet use vertical force of this to lift constant height. What is the magnitude of acceleration due to gravity at the surface of this planet? So look, you're going to have an object, right? And you're moving it. You're trying to move it up with a force of 175 newtons. But your object is moving up, but it's not actually accelerating. Now remember that net force is equal to mass times acceleration, but more specifically, net force is equal to mass times acceleration. But if there's no acceleration, there's no net force. Now, what force is also acting on this object that can counteract this lifting force, this applied force? And the answer to that is, well, the force of gravity. Force of gravity, or mass times this gravity constant, well, this also has to be equal to 175 newtons, right? Because then these 175 newtons would kind of just cancel out and there would be zero net force. So technically it's negative 175 newtons because it's in the opposite direction. But once again, this is asking for the magnitude. So honestly, the sign doesn't matter here. But 175 divided by 87.5, you're going to get this gravity constant of 2. And the reason why this gravity constant is different from this 9.8 that I talked about earlier is because we're on a different planet. 4 forces act concurrently on this block. So you can see that these 4 forces are all acting on this block. And a result of these forces, what would the block do? Well, the top and the bottom forces are going to cancel each other out. And this 120 is greater than 100 newtons. So there's going to be a net force of 20 newtons to the left. If there's a force, there's acceleration. So number 25 is D. If the magnitude of the block's acceleration is 2 meters per second, well, what is the net force? All right, so this is just another force is equal to mass times acceleration problem. We know that the acceleration is 2 meters per second, and just looking at this diagram, there's a net force of 10 newtons to the left, right? Because if there's 12 newtons this way, 2 newtons this way, then the net force is 10 newtons this way, right? Just makes sense mathematically. So if this is 10 divided by 2, mass is going to be 5. So answer choice is B for that one. What is the magnitude of force that the sled exerts on the student? this one, right? Number 27. Okay. This is Newton's third law for number 27. So let's say you're the student and you're going to be pulling on this sled, right? That's 20 newtons. So as you pull on this sled, the sled is kind of just going to be pulling back on you, right? Or sorry, this is the wrong thing. As you pull on this sled with a force of 20 newtons, the sled is also going to be pulling back on you with a force of 20 newtons. So the answer choice here is actually going to be A, believe it or not. Think about when you're doing pull-ups. Say this is the bar, and let's say that you're doing pull-ups, right? As you're trying to pull the bar down, right? Because think about if you're doing like pull-ups, right? You're trying to pull the bar down, right? You're using the force to pull the bar down, but as a result, you get pulled up. That's pretty cool. Okay. What is the magnitude of the gravitational forces between 5? Ooh, now we're talking about gravitational force. So now, gotta use this formula. The gravitational force between two different objects, right? So for this gravitational force, we're focusing on just the Earth and that object. But if we're just trying to talk about, in general, any two objects, we're gonna use this force of gravity formula. Force of gravity is equal to big G, which is this big constant, 6.67 times 10 to the negative 11 times 10 to the negative 11. And then this is going to be multiplied by, and then the rest of the formula is going to be mass 1 times mass 2 divided by r squared, which is distance. So mass 1, which is 5 kilogram, times mass 2, which is also 5 kilogram, divided by the distance squared, which is 25. So, I mean, if all of this just cancels out, number 28 has to be answer choice number C, right? Just 6.67 e negative 11, right? As a meter moves from a distance of 16 to a distance of 2, the magnitude of the gravitational force becomes what? So let's say that you're starting out with the same formula, and let's say that the distance is 16, right? But this time, what happens is that the distance goes from 16 to a distance of 2. So you're trying to find out, how does the force change as you change the distance? And sorry if this is confusing. All this should be squared because it's the square of the distance. Okay. So how would this change? Well, 16 squared, that's going to be equal to 256. 2 squared is 4. And 256 divided by 4, that's equal to 64. All right. What this is saying is that if the distance goes from 16 to 2 meters, this attraction is going to get 64 times stronger. All right. And that makes sense, right? Think about two magnets. If you move two magnets closer, the closer the distance, the stronger that attraction is going to be. And because we're dividing by the radius squared, or sorry, the distance squared, well, changing the distance actually has the greatest impact. All right. Because it's squared. So 2 kilogram object, and it's accelerating at 5 meters per second squared on a rough horizontal surface. And we want to find out the magnitude of the frictional force. Now, this problem, it's like, I'm probably going to skip this one because the text here doesn't match up with what's happening in the diagram. It's honestly like really confusing. I kind of try to do this, and then like I kind of got two answers. I got B and D, and you know, probably when encountering this, I would probably just follow the text up here. And that's probably what gets the correct, and that's what gets the correct answer. But you know, yeah, this problem is just kind of confusing. But what you do, or let's say if we're sticking to what's here on the diagram, right? So you have acceleration of 10 meters per second, and your applied force is 50 newtons, and you have some frictional force with a mass. Now you know that the net force is equal to mass times acceleration. The net force is comprised of the force of friction and your applied force, which is 50 newtons. And you know that's equal to the mass, which is 4 times the acceleration, which is 10. 4 times 10 is 40, and 40 minus 50 is 10. But the thing is that 10 actually isn't the answer, because if you do it the other way, right? So instead of let me actually alter this equation a bit. So instead of doing that, you have 2 kilogram object, so now your mass is 2, and your acceleration is 5, then, well, you're going to get an answer of negative 40 newtons, which is answer choice number D. So I know this is a very confusing question, but honestly, in this case, I would probably just stick to the text there, because that's more reliable than, at least I'm guessing that's more reliable than the picture. Okay. 8 Newton wooden block slides across. Magnitude of force of kinetic friction between the block and the floor. So for this problem, right, we have an 8 Newton wooden block sliding across some wooden floor at a constant velocity. At a constant velocity, the net force is going to be 0, right? Now, if you're applying a force, let's say if I'm applying a force. I know it doesn't say in the problem, but let's say if I'm applying a force. However, the force of friction is causing this block to be at a constant velocity. Well, this applied force and this force of friction, they have to balance out, right? Because there's no net acceleration, meaning that there's no net force. Okay. Now, if you want to find out the force of friction, that's going to be equal to the coefficient of kinetic friction multiplied by the normal force. All right. Think about when you're rubbing like a really large, or think about, let's say if you have a truck on the road and the road is like super bumpy, it's going to be a lot of friction going on. But if you have like a little toy car, well, it's probably not going to be as much friction. So of course, the weight of the object, which is related to that normal force, that's going to determine, well, the force of friction. But it's still important to note that, like, you have the force of gravity moving the object down, or trying to accelerate the object downwards, but it's balanced by the normal force. So this normal force is that force that balances the object in the vertical direction, so that it's not actually no clipping down the floor and into the Earth's center, right? It keeps the object balanced on whatever surface that it's on. So the coefficient, this is 8 newtons for the normal force, right? Because if there's 8 newtons downwards, then to balance that in the vertical direction, there has to be 8 newtons upwards. And for wood, the coefficient of kinetic friction is 0.3. So if you actually multiply these two numbers together, you should get 2.4, which is answer choice A. I'm pretty sure, but I'm just, yeah, I mean, that looks right. In the physics reference table, for the old one, they used to include the coefficient of kinetic friction for the things, but now they don't have that. So they're probably in like actual regions, they're probably going to give you like a table with the values in the actual question, so that you're actually able to do it without knowing it beforehand. So it's pretty sure you're not required to memorize random coefficients of friction for the exam. So 2 forces act concurrently on this object. One additional force would establish equilibrium 4 newtons to the left. What equilibrium basically is, like the force is balancing out, right? So 4 more newtons to the left, well, 10 and 10 will now balance out. Yes, these are the ones. Scalar quantity. Scalar, remember, only a magnitude, no direction, time, right? The way I know this is that, well, velocity is displacement over time, and displacement is a vector quantity, right? If I say that I move 5 meters to the right, that is a magnitude and a direction. So if displacement is a vector quantity, well then displacement divided by time is a scalar quantity, so it only has magnitude. Well, that's going to lead me to another vector quantity for velocity. So displacement's a vector, velocity is a vector, momentum is also a vector quantity, because I know velocity is a vector quantity and mass is just a magnitude, right? So this scalar times this vector quantity is going to give me a vector quantity for my momentum. So, once again, I kind of like said it right here, but yeah, time is going to be a scalar quantity. There's only a magnitude of time, like 3 seconds, but it's not like 3 seconds to the right. A vector quantity, well, what is a vector quantity? This is pretty tricky. Well, it's not speed. I know it's not speed and distance, because speed is only like 30 miles per hour. It's only a magnitude, right? And distance, if I say that I walked 5 meters, that's only, well, a magnitude, no direction. But what about power and force? Now, power is actually not a vector quantity. It's actually force. Let's think about why. Force is equal to mass times acceleration, and acceleration has a direction, meaning that force also has a direction, right? If you see on this, literally on this diagram, you have this force, and it's in like some certain direction, right? 10 newtons to the right, 6 newtons to the left. But power is, this is going to be the rate at which work is done. Remember that, let's say if you have like an object and you apply force to it, and let's say that the object moves a certain displacement or a certain distance. Work is defined to be equal to that force multiplied by that displacement. And work is also related to energy, because think about it. In order for you to move an object from one area to another, that requires the transfer of energy. And power is just the rate at which work is being done. So power is just going to be equal to work over time. It's just the rate at which work is done, or you can think about it as the rate at which energy is being transferred. All right, so let's do number 35 now. The vector diagram below shows the horizontal component and the vertical component. What is the magnitude of the horizontal? Well, let's say that if we're trying to find out the vertical component. The vertical component, so let's actually do this. Sine of 35, what is that equal to? Sine of an angle is equal to opposite over hypotenuse. That's equal to VF divided by 24. So VF is equal to 24 sine of 35. And make sure that you have your calculator in degree mode when you're doing this. So I got 13 point, sine of 35 degrees times 13.76, so that's approximately 14. Answer choice number D has to be the correct answer for this one. And also for the cosine, well, just remember that cosine of an angle, so cosine of 35 is equal to adjacent over hypotenuse, and you get the same thing. So the general formula is that the force in the vertical direction is going to be equal to the net force, so the original force times sine of that angle, and then the horizontal force is going to be that force times the cosine of that angle. A shopping cart slows down as it moves along the level floor. What describes the energy of this cart? So the floor is level, right? And you have something that slows down. Now, because the height isn't changing, remember that potential energy is equal to mass times gravity times acceleration due to gravity times height. If the height isn't changing, then these two things also stay constant. So the potential energy actually remains the same. However, because our object is slowing down, remember that kinetic energy is equal to 1/2 m times velocity squared. If our velocity is decreasing, our kinetic energy is also going to decrease. So number 36 is going to be C. If the speed of the moving object is doubled, then what happens to the kinetic energy? Well, if I double this velocity, then I'm going to have 2 velocity squared, which is going to be a 4 times increase. So it's going to be quadrupled for that one. All right, this is why it's important to recognize that whenever you're squaring something, this is like the square law or inverse square law, whatever it's called, it's going to have a really big impact if you only just double something, right? If you're squaring something, it's going to have a really big impact. So 1 kilogram ball is dropped from the top of a building just before striking the ground at ball speed is this. What is the gravitational potential energy? So the important thing to know is that the potential energy at the top is equal to the kinetic energy at the bottom for this. Assuming that the forces are conservative. All right, so there's no air resistance, there's no any types of friction, so we're not losing any of this potential or kinetic energy. And that means that if you have a ball that's all the way on the top here, all that potential energy is going to get converted into kinetic energy, right? Because originally your object has 0 kinetic energy, it was at rest, but it had a lot of potential energy, a lot of stored energy due to this height. And then when it fell down, all that potential energy was converted into that speed or that velocity. So you're maximizing kinetic energy at the bottom, and you're maximizing potential energy at the top. So what's the kinetic energy at the bottom? That's going to be equal to 1/2 times the mass times the velocity squared, which is 12 squared is 144. Therefore, kinetic energy at bottom, which is 72, has to be equal to the potential energy at the top. All right, which is going to be answer choice number C. Which statement describes kinetic energy and total mechanical energy of a block as it gets pulled on at a constant speed? So if a block on an incline gets up at a constant speed, kinetic energy does not change, but the let me see. Okay. So the total kinetic energy right? It remains the same, but the mechanical energy is equal to the kinetic energy plus the potential energy. Now, if you're pulling a block up an incline, the potential energy is, of course, increasing. So that means the mechanical energy is also going to be increasing, which is why number 39 is C. All right. So in this case, when you're pulling a block up an incline, the mechanical energy is not conserved. Whenever you're dealing with things like friction, air resistance, I'm just going to put AR for air resistance, and even just applied force. Whenever you're applying a force, that's changing the mechanical energy of whatever object you're dealing with. Ooh, this one. Remember, the equation for elastic potential energy, aka the potential energy of that spring, it's 1/2 times kx squared. K is the spring constant. It measures basically how stiff the string is, while x is how far you stretch it. So how far you stretch a spring and how hard it is to actually stretch that spring is going to be kind of affecting that potential energy, that stored energy. That's why if you stretch like a slinky, for example, super far, you'll find that it bounces back, right, really fast. There's like a force, if you have like a spring, there's a force, where you kind of stretch the spring, but at the same time, there's going to be some sort of restoration force that tries to pull the spring back to its equilibrium position. And all that's related to Hooke's law and everything. So potential energy, 1/2 times K times 0.25 squared. I'm just plugging this into the calculator now. So I got that my spring constant is actually, what is it? It's actually D. All right, so that is going to be the answer, right? Because 2.34 divided by 0.03125, that's 74.88, which is approximately 74.9. A student performs a laboratory investigation to determine the spring constant of a spring, and then the force applied to the spring was varied and the resulting elongation of the spring was measured. What is the spring constant for the spring? Okay. This is where you got to use the brain, and there's something really cool that you can do. What's the unit for the spring constant? The unit for spring constant, you can see in all these answer choices, that's Newton divided by meters. This is the only one with Newton divided by meters. Wow, that's pretty funny. But another way you can do this is, right, remember that if the spring constant is basically just saying, how many newtons do I need to stretch the spring by 1 meter? Well, if it takes, let's say, 4 newtons to stretch the spring by 0.2 meters, then that corresponds to 20 newtons for 1 meter, which is why answer choice number D makes the most sense. How much work is required to lift a 10 Newton weight from 4 meters to 40 meters above the surface of the Earth? Remember that work is equal to force times displacement. In this case, I have to move a 10 Newton weight. So remember, weight is just the force of gravity on the object, and it is a force. And I have to lift this 10 newtons an extra 36 meters, right? Because I move it from 4 meters to 40 meters. So the displacement or the distance is 36 meters, and therefore C would be our answer. Diagram shows 50. The crate is pushed at constant speed from point A to point B. If the angle, what would be the effective magnitude and the total work done on the crate as it moved from A to B? So this problem is pretty tricky. You would think that because the distance from A to B is constant, you would think that the work would remain the same. But what is work comprised of? Force times displacement. So if the force decreases or increases anyway, that would also affect the work in the same relationship. So if the work increases, but the magnitude of F decreases, that would imply my displacement or my distance increases. But obviously that's not the case. Our displacement remains constant. So this is like a contradiction, right? So the only answer choice that makes sense is D, right? If force increases, assuming a constant displacement, then my work has to go in the same direction as the force. The reason why D is actually the correct answer is, well, think about it. If I have a bigger angle, then of course that's going to take way more work, right? Because now gravity has more of an effect on the block, right? Because that slope is steeper for that object. And some formulas that are pretty important to know is that given a block like this with an angle, and let's say you have a block here, the direction of gravity that actually pulls the block down, that's going to be mg sine of that object, sine angle. Meanwhile, the kind of normal force, you can think about it, or this force that kind of is perpendicular to this object, right? That's why it's called normal force, because normal is perpendicular. That would be mg cosine theta. So the force, you can think about it as the force in the x direction, the direction that actually pulls the object downwards, is equal to mg sine theta. Now, what is force also equal to? Force is also equal to mass times acceleration, and I'm just going to say an acceleration in the x direction, right? So this mg sine of theta is also equal to mass times this acceleration in the x direction. The masses cancel out, so you actually get that the acceleration in the x direction is only dependent on the angle that the object is on. And the higher the angle, well, think about it, as the angle increases, sine of theta increases, so the object is going to be accelerating more downwards, meaning that if the acceleration that goes downwards increases, you're going to need more force to try to move that object upwards. The angle is bigger. A 44 Newton girl, or 500 Newton girl, lifts a 10 Newton. Actually, how many pages do I have left? I only have, yeah. Oh shoot, there's actually a lot of pages left. Oh boy. A 55 Newton girl lifts a 10 Newton box vertically upwards, the distance of that. What is the work done on the box? Work is equal to force. In this case, it's the box times this. So number 44 would be A. Constant speed, horizontal. So student blows a box on a horizontal floor at a constant speed of 4 meters per second by exerting a constant horizontal force of 45 newtons. So how much force does the student do against friction in moving the box 5.5 meters across the floor? Well, once again, work is equal to force. So in this case, our force is 45 newtons times that displacement, which is 5.5. And you would get approximately 250 joules for that one, right? Now, a mortar lifts this guy 10 meters in 8 seconds. And what is the minimum power generated by the mortar? Okay. Remember that this mass right over here, you can convert that into a force, right? Whenever you have this kilograms, you can convert it into a force through the force of gravity. Remember, the force of gravity is equal to mass times that acceleration due to gravity. So 400 times 9.8 is 3,920 newtons, right? Now, force, this is our force, right? Force of gravity. Force times displacement, 10 meters, is equal to work. And remember that work divided by time, 8 seconds, that's equal to power, right? So everything here connects together. So 3,920 times 10 divided by 8. Divided by 8, I get 4,900, and that's answer choice number C. Okay. A baseball starts with an average force of that many newtons. Actually, let me just erase all of this so everything's clear. A baseball bat strikes a ball with average force of this many newtons. If the bat stays in contact with the ball for this many meters, what is the kinetic energy that the ball will require? Now, this is the trick that no one's going to tell you except for me. All right. What is the unit for joules? Remember, work is equal to force times displacement. And that is a unit of, well, force is a unit of newtons, distance is a unit of meters. And remember that newtons has a unit kilograms times meters per second squared. So in conclusion, joules has the unit of kilograms times meters squared divided by second squared, right? This is the unit for work, potential energy, kinetic energy, all types of energy. That's measured in joules. Now, even if you have no idea what to do, well, you just remember that, well, whatever answer that you're going to be ending up with has to have a unit of kilograms times meter squared divided by second squared, because all of this is in joules. So you just look at the units. Well, I have a newton, I have a meter. That leads me to the correct unit. So if you just multiply out these two values together, you're just going to get answer choice number A. That's kind of how you can like cheat the multiple choice, quote unquote. Okay, so a pendulum is made from this mass attached to a rope to the ceiling. Mass is pushed to the side until it is at position A. And then after that, it is released and then it moves between point A and B. What is the total amount of kinetic energy that the mass has as it swings freely through its equilibrium position? So when I release this, how much kinetic energy does it have? We're going to use the same principle. Kinetic energy at bottom is equal to potential energy at the top. What's the potential energy at the top? mgh, right? Mass times this times the height, which is 1.5. 7.5 times 9.5 times 1.5, that's 106. It's 106, so that is approximately, for our answer choice number 48, pretty sure that is C, if I am doing my maths correctly. So number 49, as a block slides across the table, the speed decreases or the temperature increases. What's the change? Well, if the speed is decreasing, that means that this block has a lower kinetic energy. So I'm going to eliminate these two. Now, what's the internal energy? Internal energy basically describes like the particles of the block. So if you just like focus on like the atoms in this block, right? The atoms themselves also have kinetic energy and potential energy. So kinetic energy of the actual block is actually different from the kinetic energy of the particles and their potential energies. When we're talking about, these microscopic things, this actually refers to the internal energy of the block. So in this case, because our temperature increases, well, that's actually going to cause an increase in the internal energy because these particles are actually going to start moving faster. So even though the block itself is slowing down, the particles are moving faster, meaning that the internal energy is actually going to increase. As the object slides down the incline, the sum of the gravitational potential energy and the kinetic energy of the object will blink. Now, what's important here is the fact that this object is on a frictionless incline, meaning that this energy is not going to be lost. So imagine if there was friction, well, the object will actually not go as fast as it would if it was frictionless. So because this object is going down, potential energy decreases, but to counterbalance that, kinetic energy will increase, meaning that the sum, which is the mechanical energy, will remain the same. So a ball is thrown horizontally with initial velocity of 20 meters per second at this tower, 60 meters. And we want to find out the horizontal velocity when the ball, before it reaches the ground, and we're neglecting air resistance. Now think about it. This ball is moving sideways, but because it's encountering no air resistance, this horizontal velocity is actually going to remain the same. So the answer choice is going to be B for number 51, because the only thing that's changing about this ball is that the velocity is increasing downwards. But if there's no air resistance, remember that the horizontal component is completely independent from the vertical component. So it's going to fall down faster, but the horizontal component is going to stay the same. They are simultaneously thrown from the same height. Red ball has initial speed of 40 and green ball initial 20. Compared to the time it takes for the red ball to reach the ground, the time it takes for the blue ball to reach the ground will be what? Once again, it's going to be the same because it's thrown horizontally. So it's like throwing two balls. It's going to land at the same time because it doesn't matter how fast it's moving in the horizontal direction. If the vertical velocity starts at rest, acceleration due to gravity is constant, they're all going to fall to the ground at the same time. So a golf ball leaves a golf club with this at an angle of 40 degrees. What is the horizontal distance traveled during the first 2.1 seconds of its flight? So we want to find out, first of all, this velocity in the x direction. And remember how you find out the velocity in the x direction, right? It's just going to be 40 times cosine of this angle, cosine of 40. 40 times cosine of 40 degrees is approximately, I'm just going to say that's 30, and 30 meters per second is my initial velocity in the x direction. And remember that this is a constant horizontal velocity because we're assuming that there's no air resistance. Remember that velocity is equal to displacement over time. So to find out the displacement, or the distance in this case, velocity times time. So velocity times this time. And I get 63, which is approximately C for number 53. Number 54, this guy uses a bow to fire two similar arrows using the same string force. One arrow is fired at an angle of 60, and the other's angle of 40. Compare angle has 60 is what? So this is one where you kind of have to pay attention to the angles, of course. So you have one that's fired at 60 degrees, which is a bigger angle, and one that's fired at 45 degrees. Now you would expect that the arrow that's fired at 60 degrees, well, that's going to go higher, obviously, because it's at a higher angle, but it's not going to go as far. Well, the arrow fired at 45 degrees might go a little bit further, but it's not going to get as high. So if the angle is closer to 0, it's pointed more towards the ground, it's probably going to cover more distance, but it's not going to be at a really high peak. Meanwhile, if you just like shoot the arrow all the way up 90 degrees, that's going to get the maximum height. That's not going to get the maximum range. So compared to angle arrow fired at 60, the arrow fired at 45, well, that's probably going to have a shorter flight time because it's not going to get as high, but there's going to be a longer range. So number 54 would be C, lines up with what I said. 55, this guy jumps straight up to grab a rebound. If this guy was in the air for 0.8 seconds, how high does she jump? So this one, we can take advantage of two things. So recall that at the highest point, the velocity in the y direction is going to be equal to 0. But another factor that we're going to take advantage of is if you're jumping up, right, the time it takes to go up is equal to the time it takes that you go down. Time up is equal to time down. So if this guy was in the air for 0.8 seconds, that means 0.4 seconds was spent coming up and 0.4 seconds was spent going down. So that means that if we took 0.4 seconds to go up, this is also the time when your vertical velocity is equal to 0. To take advantage of that, we can say that, let's just say, I don't know, my final velocity, which is equal to 0, is equal to my initial velocity plus acceleration, which I know is negative 9.8 times the time, 0.4. And if I solve this, I'm going to get 3.92 as my initial vertical velocity. Once I have my initial vertical velocity, then I can solve for my displacement, because I know that my displacement is equal to initial velocity times time plus 1/2 at squared. 0.4 squared. So 3.92 times 0.4 plus 1/2 times a times t squared. And I get 0.78 as my answer for number 55. A projectile is fired from a gun near the surface of Earth. The initial velocity has a vertical component of 98 and a horizontal component. How long will it take the projectile to reach the highest point? So we basically want to find out, we know that at the highest point, right? Once again, vertical velocity is equal to 0. We know that the initial vertical component is, initial velocity is 98 meters per second. And we want to find out the time it takes. So once again, Vf is equal to initial velocity plus acceleration times time. And then solving for t, I get answer choice number B there. For number 57, this is some centripetal thingies going on because we're talking about circles. So we have an unbalanced force of 40 newtons that keeps a 5 kilogram object traveling in a circle of radius 2 meters, and we want to find out what is the speed of the object. So the formula for centripetal force is equal to the centripetal acceleration, the mass times the centripetal acceleration. And centripetal acceleration is equal to the velocity squared divided by the radius. So first, let's solve for the centripetal acceleration. We can do that by taking my centripetal force, which is 40 newtons, and we divide it by the mass, which is 5 kilograms. And that gives us the centripetal acceleration. 40 divided by 5 is 8, and we know that's equal to v squared over r, and we know that the radius is 2 meters. So 8 times 2 is 16 is equal to v squared, and then square root both sides, and I get 4. So 57 is 4. 58, this ball at mass m is at the end of a string, or I'm just going to try to delete everything. A ball of mass m is at the end of a string, and it's swinging a horizontal circular path with radius r. Which combination of changes will require the greatest increase of the centripetal force acting on the ball? This one is just another problem where you can just kind of just look at the formulas. So I know centripetal force is equal to centripetal acceleration times mass, but I'm just going to write it as v squared over r here. Now, which one of the following will increase the force the most? If I decrease my denominator and increase my numerator, that would increase my force, right? So increasing v, but decreasing r, having r, that would be the highest centripetal force acting on the ball. All right. So, I mean, this also makes sense because imagine if you're like on a racetrack, or maybe think about it as like, I don't know, like a solar system, right? You're going to need something in the middle, let's just say like a planet, to keep this orbit in check. Now, if the planet moves faster, of course, you might need a little more force to actually keep this planet in check. And likewise, if your radius is smaller, well, you're also going to need more force to keep this in check, because now the path that the thing travels around is less. So it's kind of like easier for it to escape, if you will. Well, if this planet was further away, so instead of this, I have like, I don't know, like a bigger circle, for example, right? You can see that I don't need as much force to keep this planet in check, because it needs to kind of travel a longer path. So there's more time for this planet in the center to kind of pull it towards itself. So there's more time for this planet in the center to, change the path of my object. All right, final stretch. So this kilogram car travels at a constant speed of 20 meters per second around a horizontal circular track, which diagram correctly represents the car's velocity and the direction of the centripetal force. Remember, centripetal force always points towards the center because it's at the same direction as the centripetal acceleration, but the velocity is going to be tangent, or it's going to be traveling in a tangent direction. So number 59 would actually be A. All right, remember that, like, once again, let's say if you have a planet here, think about it as the planet wants to move out of the orbit, but you have this centripetal force inside pointing to the center that always curves the path so that this planet never actually escapes the orbit. And finally, a student on her way. Oh, yes, the displacement. So remember that the distance traveled 4, 3, 4. Well, that's a total of 11 blocks. That's the total distance. But the displacement is just, you can think about it as the shortest path from the school to this home, right? Think about it as like sort of like the net distance, if you will. So what's the net distance? Well, it's composed of this 8 block. And actually, I can solve for the displacement. So what I can do is I can set up a triangle, right? Where this side right over here is going to be kind of like the shortest path, my net distance. This side of my triangle is 8 blocks in total, right? Because 4 plus 4 is 8. And this side right over here is 3 blocks. So I can just Pythagorean theorem this out. I get a squared plus b squared c squared. So 64 plus, I'm going to say 9, 73, and then the square root of 73 is about 8.5. So you can see that my displacement is going to be less than the distance. And there we have it. That is the full physics midterm review. And here are like the answer key. I just kind of like placed it at the side. If you kind of did all this and then you want to like check the answer.